All right, so today we're diving into something, well, it's pretty mind-bending. We're talking about how AI is basically helping us read the universe's secret instruction manual. You know, the fundamental rules that run everything. We're going to look at how machine learning is cracking these incredibly tough codes that have stumped scientists for ages, and in the process, totally unlocking the future of physics. So yeah, let's get right into it.
So let's start with a really big question, one that affects all of us. I mean, how do we predict a hurricane's path, or figure out how to design a faster, more efficient airplane? It even comes down to things like how heat spreads through the chip in your computer. How do we figure all that stuff out? What's the underlying secret?
Well, it turns out the secret is that everything, and I mean everything in the physical world, from a tiny ripple in a pond to the orbits of entire planets, it all follows a specific set of rules. It's kind of like there's this grand hidden instruction manual for the universe, and it's all written in the language of math. And here's the kicker. If you can learn to read that manual, you can basically predict the future.
Okay, so let's crack open that instruction manual, shall we? We're going to start with the universe's hidden rules, basically understanding the math that actually describes reality.
Now, I know that sounds intense, but don't let the name scare you off. Partial Differential Equations, or PDEs for short, they're really just the language, the grammar of that cosmic instruction manual. The easiest way to think about them is like a recipe that tells you exactly how things change, both over time and across space. And trust me, these things are absolutely crucial for modeling pretty much everything.
But of course, there's a catch. Just because we have the rule book, that doesn't mean it's easy to read. Not at all. In fact, trying to actually solve these equations, well, that's been one of the single biggest hurdles in all of science. It creates this massive, massive computational bottleneck. And I'm not exaggerating when I say this, has been a problem for centuries. For the longest time, trying to solve these PDEs was like trying to untangle an infinitely complicated knot. Even with our best methods, we were just getting approximations, and those methods had some serious limitations that held back progress in tons of different fields.
So you end up with this huge disconnect, right? On one hand, you have the traditional methods, which are just immensely complex. They require massive supercomputers, and they are painfully slow and super expensive. But on the other hand, we desperately need faster predictions and cheaper simulations. So we were stuck. We knew the rules, but we couldn't read them fast enough. Something had to change. We needed a totally new approach.
And that new approach? It's here. This is where AI enters the equation. It's a whole new tool that's letting us finally crack this incredibly tough code.
So how does it work? Well, AI helps in three pretty incredible ways. First, it can learn to just guess the answer, basically. It looks at a ton of data and predicts the solution directly, totally skipping all the brutal math. Second, and this is really wild, it can work backwards. It can look at a bunch of data from an experiment and figure out the underlying physics for us, even if we have no idea what the rules are. And third, it can be a fantastic assistant. It can help our classic solvers run way faster by cleaning up their work on quicker, rougher simulations.
And just to be clear, this isn't some far-off science fiction idea. This is happening right now. So let's take a look inside the lab and see how this stuff is actually being used. We're going to check out 4 cutting-edge techniques that are being developed at the Mechanical and AI Lab, also known as MAIL.
All right, first up, we've got something called graph neural nets. The main idea here is pretty cool. Instead of looking at a problem on a stiff, boring grid, it treats the physical space, like, say, the air flowing over an airplane wing, as a flexible, connected network of points. Think of it like a social network, but for particles and forces. It's a totally different way of looking at the problem.
And this approach is amazing for speeding up really complex simulations. For fluids or molecules. It's also great for digging through messy, real-world data that doesn't fit neatly into a grid. By thinking about the world as a network, we're unlocking a whole new level of understanding. It's a total game changer.
Okay, technique number 2, neural operators. Now this is a little different. Instead of just learning to predict a single answer, a neural operator learns the entire method for solving a problem. It's like, instead of memorizing one math problem, it learns the formula so it can solve a whole category of them. It's learning the how-to guide.
And get this, the tech they're using for this is fascinating. They're actually using transformer models. Yeah, that's the same kind of AI architecture that powers tools like ChatGPT. But instead of learning human language, they're teaching it to learn the language of physics. I mean, how cool is that crossover?
All right, our third technique, symbolic representation.
This one might be the most mind-blowing of all. Because here, the AI isn't just solving an equation that we give it. No, it's looking at raw data from an experiment and trying to discover the equation itself, completely from scratch.
This is basically like giving a scientist a super-powered research partner, an assistant that can sift through mountains of data, spot patterns no human could ever see, and then suggest entirely new laws of physics. It shifts AI from being just a really fast calculator to being a genuine, creative partner in the process of discovery.
And last but not least, technique number 4 is called super resolution. You know in spy movies where they have a blurry image and someone just yells, "Enhance," and it magically becomes crystal clear? Well, that's basically what this is, but for scientific data.
So what it lets scientists do is run a really fast, cheap, low-res simulation, and then they use AI to intelligently fill in all the missing details. It upscales that blurry picture into a super sharp, high-fidelity model. This is huge for things like reconstructing chaotic turbulence, something that used to be way too expensive and time-consuming to compute properly.
So, okay, let's take a step back and look at the big picture here. With all these incredibly powerful new tools in our arsenal, what does this all mean for the future of science? Are we actually on the brink of solving problems we once thought were unsolvable?
I think this really says it all. We're no longer just solving equations. We're teaching AI to discover them. See, that's the fundamental shift right there. This isn't just about getting faster answers to the same old questions. We're building tools that can help us discover entirely new questions to ask. It's a leap from pure calculation to actual discovery.
And why does this matter to you? Well, think about it. This means faster, way more accurate climate models. It means designing more efficient solar panels and wind turbines, creating revolutionary new materials we haven't even dreamed of yet, even developing personalized medicine by perfectly simulating blood flow in a patient. Literally any field that touches physics is about to get a massive, massive upgrade. And that kind of brings us to the final big thought here. For hundreds of years, our understanding of the universe was bottlenecked, really, by our ability to do the math. But now with AI as a true scientific partner, that old limit is just being completely erased. So the question we have to ask ourselves isn't if we're going to solve the next great scientific mystery, it's which one will it be? With these tools, what part of our world are we finally going to understand next?